Good afternoon. I'm very happy that all of you are here to listen to the talk by Satwik Bhattamishra. Satwik is a PhD student finishing, I guess, in the fourth year at University of Oxford, and like Satwik was recommended to visit our department because of his supervisor, Phil Blunson. So if you know Phil from many years ago, Phil was here on that famous year when the Iceland volcano had their eruption, closing the all air traffic across Europe for 2 weeks in total. And Phil had to spend here not just the single Monday for the seminar, but 1 week extra until he was able to board on a bus and go back to the UK on the standard route. And I hope that there will be no eruption in the volcano, but should that happen, you will probably be not so much bothered as Phil was, because you're here also with for personal links. And for your topic, which is very relevant to what many people are studying at the department, you're going to tell us something about the limitations of transformers and recurrent architectures with respect to their representational abilities, and maybe also some of the in-context learning. What else to add? You're not just at Oxford, you have spent, and maybe you're still supported by Google DeepMind, and you have worked for Google and maybe other labs, and Cohere as well, where Phil is, right? So you have also hands-on experience. It's not just theory, it's also training and improving the models. Satwik, so the floor is yours.
Yeah, thank you very much for the introduction. So I think I'll get started. So hi everyone, thanks for coming. It's a pleasure to be here. And today I'll talk about some of our work on understanding the representational capabilities of transformers and recurrent models. So as you may know, in the past decade or so, there have been a few paradigm shifts in the way people or researchers model language. So before 2013, researchers typically used hidden Markov models, weighted automata, and so on. And around 2014 or 15, LSTMs became more popular, and LSTMs kind of became like the go-to architecture to model language. And around 2018 is the time when transformers started to supplant LSTMs. This is around the time that BERT and Roberta came out. And since 2021, there has been a lot of effort to revive recurrent models. This is primarily because the inference time of transformers is quadratic with respect to the sequence length. And for recurrent models, it's linear. And as these models are being more widely deployed, the inference time has become a lot more important than training time. And given how ubiquitous these models are, it is natural to ask some very basic questions, like what kind of functions can transformers or recurrent models compute? And this is a quite broad and vague question, but it can be broken down into 3 relatively more concrete questions. So the first question that one might ask is, what kind of functions can they theoretically represent or express? So this involves questions like, does there exist a transformer that can do addition? Or does there exist a recurrent model that can do multiplication up to, say, 10,000 digits? And so on. So if you can prove that transformers can express a function, it doesn't necessarily mean that they can learn it. But if one can prove that they cannot express a function, then it implies that they naturally cannot learn it as well. Which brings us to the next question, which has perhaps been the most challenging one, which is understanding what kind of functions can they provably learn under certain assumptions. And the last one, but perhaps the one that we care about the most in practice, is what kind of functions can they learn empirically. If we actually generate some data, train transformer or LSTMs with standard optimizers, then what kind of functions can learn well? And a very natural related question is, what are the differences between these different architectures? So are there some problems which are easier for transformers but difficult for recurrent models, or vice versa? And in the long term, what we are also interested in is understanding the implications of these kind of analysis on practical tasks. And another thing we might be interested in is understanding whether such analysis can aid us in designing better architecture. So maybe I'll talk about this a little bit. So a natural starting point to understand this question is analysis on formal languages. Because we want to kind of characterize the kind of functions that these sequence models can capture, we need a framework to define functions precisely over sequences. And formal language theory provides us with such a framework. And analysis on formal languages basically means understanding the ability of these architectures like transformers and RNNs to recognize various regular languages, contextual languages, and so on. And the problem statement is very simple. So for a formal language L, we want to understand when a transformer is given a sequence S, it has to classify, or whether it can classify whether the sequence S belongs to the language L or not. So just some basics about formal languages. So this is a figure that most of you must have seen at some point. So this is the Chomsky hierarchy, which categorizes different classes of language into 4 different classes, where regular language is the lowest class. So it contains languages that can be recognized by a finite state automaton, and then you have contextual languages which can be recognized by pushdown automaton, and so on. So one thing to note about this class is that regular language contains all languages that can be recognized with a finite amount of memory. And beyond regular language, all classes like say contextual language require an unbounded stack. And of course, the context sensitive and so on are naturally even more complex. So just as an example, let's look at a regular language. So this the parity language, which has been relatively more influential in the context of analyzing sequence model. So parity language is very simple. So it contains sequences of zeros and ones. So it's a sequence of bits. And given a sequence of bits, you need to check whether the number of ones is odd or even. So, and the number of zeros do not matter. So if the number of ones is odd, then it's in the language. And if the number of ones are even, then the string is not in the language. So this is a very simple language which can be recognized by a 2-state DFA. And we'll revisit this problem a few times. And then you have contextual languages, where the most notable one is the family of Deek languages, which contain strings of parentheses. So it can have multiple types of parentheses, and a string is in the Deek language if it's well balanced. So this kind of analysis on formal languages has been done quite a lot, particularly in the late 80s and in the 90s. Researchers did a lot of work to understand traditional form of recurrent models, which are not used nowadays, but they were kind of the precursors to current RNNs or LSTMs and SSMs. There's even a book about it in 2001, which summarizes a lot of work that was done in the late 80s and 90s. But after LSTMs became more popular around 2013 or 14, researchers started to revisit this line of work, and they tried to understand LSTMs through this lens of formal language theory. And in a very simplified manner, what researchers found was that LSTMs can both theoretically and empirically, they are very good at modeling regular languages and certain kind of context-free and context-sensitive languages, all of which can be categorized into something called counter languages. So the exact definition of counter languages is not important here, so I'll skip it. But essentially, it contains languages that you can recognize with some form of counting mechanism. And what researchers found is that LSTMs, they're theoretically capable of representing these kind of counter languages. And if you try empirically on a bunch of languages and you train LSTMs, then they were very good at modeling these kind of counter languages. So about 5 years ago, we tried to understand transformer through this lens of formal languages. And what we found is that while they are theoretically capable of expressing counter languages, and empirically they were very good at modeling many of these context-free and context-sensitive languages, but unlike LSTMs, they struggled a lot on modeling certain kind of regular languages. So it's not like they were horribly bad at modeling regular languages. They were bad at certain kind of languages called non-star-free languages. So even if regular language is the lowest class in the Chomsky hierarchy, the class itself has a rich hierarchy within itself. So broadly, you can categorize regular languages into 2 halves called star-free and non-star-free languages. So formally, star-free languages contain the set of languages that can be represented by regular expressions without the clean star operator, but you can ignore that definition. So intuitively, what matters is that star-free languages cannot have languages which involve any kind of modular counting or periodicity. For instance, the parity language that I mentioned just a bit ago. So for the parity language, given a string of bits, you need to check whether the number of ones is odd or even. So that involves modular counting with respect to 2. And you can construct many such languages with modular counting with respect to 3, 7, or you can have many more symbols. So all of those are non-star-free languages. and not star-free languages. And transformers, they particularly struggled at modeling many of these non-star-free languages. So this is a subset of some results we had from a paper 5 years ago. So in this table shows the performance of transformers and LSTMs on a bunch of formal languages. And the table has been divided into two parts, where the first half contains a bunch of star-free languages. The second half contains a bunch of non-star-free languages. And for each architecture, like transformer and LSTMs, we have two columns, where the first one, in distribution, is the performance of these models on strings of the same length as seen during training. And the second column contains the performance of the model on strings of higher lengths than those seen during training. So if you look at the column for LSTMs, then LSTMs, even very small-sized LSTMs, are very good at learning all these regular languages. But for transformers in particular, even though they generalize very well on star-free languages, they perform quite poorly or generalize quite poorly on non-star-free languages. So let's look at an example of why this happens to gain some intuition. So we'll look at parity and try and see how RNNs or transformers might do it. So for recurrent models, the main thing to keep in mind is that the general formulation is as follows. So all recurrent or state space models, they have a hidden state vector of fixed size, which is typically called ht. And they sequentially get input vectors, x1, x2, and so on. And given an input vector xt, given that and the previous hidden state ht minus 1, it computes the next hidden state ht. And based on the final hidden state, then it produces the output. So generally, the transformation is based on some kind of feed-forward network, and different architectures do it differently. For LSTMs, they do it in a certain way. New architectures do it in a different way. But this is sort of like the general formulation of how RNN or SSMs work. And for the parity problem, they'll get a sequence of bits, and they need to check whether the number of ones is odd. So it's straightforward to see why or how a recurrent model can do it pretty easily. So you can just consider an RNN, which has a hidden state of dimension 1, so it's a scalar. It can even be just 1 bit. And it can start with an initial hidden state with value -1. And every time it gets a 1, it can just flip the value in the hidden state from -1 to +1. And when it gets a 0 as input, it can ignore it. And whenever it gets a 1, it will keep flipping it. And at the end, based on the value in the final hidden state, it can compute or determine whether the number of ones in the entire string was odd or even. And with this simple method, they can basically do it for any arbitrary length, whether this length of the sequence is a billion or trillion. But for transformers, on the other hand, it's not very obvious how they can do it. So if you look at transformers, just for simplification, if you look at one layer of transformer, then you have the attention block followed by the feed-forward network. And the transformer, when it gets a sequence, let's say you get a sequence of 1 billion bits, but the attention block has to process all of it in parallel. Transformer doesn't have any memory vector which it can update. And based on the weighted sum or a convex combination of these input vectors, the feed-forward network then has to figure out whether the number of ones is odd or even. And this is not as easy as the case for RNNs. So this is not a proof. This is just a sketch of the intuition behind why it's difficult for transformers. But around the time a paper came out in 2020, there was another excellent paper which formalized this intuition and showed that fixed-size transformers cannot recognize parities. So after our paper came out, there were multiple follow-up works which tried to empirically understand the difference between transformers and recurrent models. And they also found that transformers struggle on a bunch of these formal languages and algorithmic tasks compared to RNNs. And there were even multiple works which provided theoretical justification behind why this happens. And given these observations, it's quite natural to ask, why do we use transformers then? If transformers are worse than recurrent models or LSTMs in modeling many of these formal language or algorithmic tasks, then why do we use transformers to build LLMs? So this is a question that I had asked many researchers a few years ago, and there were generally two types of answers. So the first possibility was that these other recurrent architectures haven't been tested properly at scale. So if you were to actually build LLMs with LSTMs and you tune them properly, then they might as well work as good as transformers or might even outperform transformers. So this is something that even one of the authors of transformers mentioned. The other possibility is that these formal language results that I mentioned are not indicative of performance on real world tasks. So the fact that transformers are bad at modeling parity might have nothing to do with how they perform on tasks like summarization or question answering. Okay. So feel free to ask any questions if you have in between. So regarding the first point, which is whether that these models haven't been tested properly at scale, so that is something that we explored. So a couple of years ago in 2023 and also last year, I worked at Cohere, where my job was essentially to build LLMs with non-transformer architecture. And the objective was to kind of implement the state-of-the-art non-transformer architectures like long convolutional models and linear RNNs at that point, and implement them and train them and tune whichever hyperparameters which are relevant and get a performance which is as close to transformers as possible. And when we did that, what we observed was that while at small scale, when you look at models with 100 million or 200 million parameters, then this non-transformer architecture achieves similar perplexity to transformer or cross entropy or perplexity. But as you scale the model from when the models have 1 billion or 7 billion parameters, 7 billion was pretty decent a couple of years ago. But at 7 billion scale, we could observe a consistent difference where transformers were always slightly better in terms of perplexity than these non-transformer architectures. And this also holds with relatively more recent models like Mamba and Mamba 2. And so first of all, at 7B, transformers had slightly better perplexity. And then when we actually took a properly trained base model, when we trained these models with 700 billion tokens, and we did evaluations on standard downstream tasks for base models, then what we found is that while these non-transformer architectures performed similar to transformer on many of these downstream tasks like summarization and question answering, they were particularly worse at certain kind of tasks like which involved extraction. So if you look at the last two columns here, movie title extraction and job title extraction, so these are tasks where the architecture or the LLM is given some text, and at the end, it is given some query based on which it has to extract some movie title or job title. And on these kind of tasks, transformers were consistently better than some of these non-transformer architectures. So based on these observations, we created another synthetic task, so which I'll describe now, where models are required to emulate the nearest neighbor algorithm. So this is a synthetic task, not for LLMs. These are for models trained from scratch, similar to the formal language tasks. So in this task, the models are given a sequence of vectors which contains pairs of inputs and labels. So the sequence of vectors is something like x1, y1, x2, y2, and so on. And at the end, there's a query vector xk. And given this sequence of vectors, the model has to find the nearest neighbor of the query vector xk. Suppose that is xj, so among the xi's, suppose xj is the nearest neighbor of xk, then the model has to produce the corresponding label yj as output. So in order to do this task, the model has to sort of simulate the nearest neighbor algorithm. So this is similar to like next token prediction task, and you can train any autoregressive model on these tasks, whether it's like transformer, LSTMs, or any other sequence model. So we synthetically generated a bunch of data, and we trained transformers and many other models like RetNet, HYNA, state space models, and so on. And this is a result from one of our papers from ICLR last year. And when we did the experiment, we found that transformers performed much better than all other non-transformer architectures on this task. And I'll quickly talk about another related work. So this is an excellent paper which was published in the same venue called Zoology. And in this paper, they introduced a task called multi-query associative recall. So this is very closely related to the nearest neighbor problem that I mentioned. It's like a subset of the problem. Yeah, so it's very interesting for certain reasons. So in this problem, a model is given a sequence of key value pairs. So these letters are the keys like A, B, C. These are the keys, and the numbers are the values like 4, 3, 6, and so on. And given a sequence of key value pairs, followed by a sequence of queries, a model is required to produce the corresponding values. For instance, when you're given A, you produce 4. When you're given C, you produce 6, and so forth. What is more interesting is why they created this task. So the authors also trained transformers and non-transformer based language models on standard language modeling datasets. And they also observed a similar perplexity gap between transformers and recurrent models and long convolutional models, but they observed a perplexity gap between transformers and non-transformer architectures. And what they did was they manually looked at the text when non-transformer architectures were achieving worse perplexity. So they manually eyeballed the text and tried to figure out why non-transformer models were struggling or where they were struggling. And based on those manual inspection, what they found was that recurrent models primarily performed poorly or got worse perplexity on text where the model was required to emulate this kind of multi-query associative recall behavior. And based on that observation, they created this synthetic task, and they trained transformers and these non-transformer architectures, and they found that transformers performed much better than non-transformer architectures. Okay, so just a quick recap of what we have discussed so far before I move on to the next part. So far, what I've tried to argue is that transformers struggle at modeling certain kind of formal languages compared to recurrent models, but at the same time, transformer-based LLMs achieve better perplexity than current recurrent models or state space models. And the transform-based LLMs, they perform better on certain kind of extraction or associative recall task. So if anyone has questions, feel free to ask.
The models are created by training on empirical data?
Which one? All of these? Yeah.
Both, I mean, the transformers and non-transformers.
Yeah.
Yeah, because if you try to, say, wire the function into both models, we probably get the correct result in both cases.
Yeah, but that's a different thing. This is not about wiring. This is about training the models on these kind of tasks. Okay, so now I'll talk about work we had from NeurIPS last year. So in this work, we tried to theoretically understand the differences in the representational capabilities of transformers and recurrent models or SSMs. And part of this work was motivated by some of these empirical observations we had on associative recall tasks and extraction like tasks. So for the rest of the talk throughout, whenever I mention a result about transformer, it applies to the most standard definition of transformer, which involves an attention block followed by a feed-forward network. And whenever I mention a limitation of transformer, then it also applies to transformers, so it also covers things like layer norms, residuals, or any type of feed-forward network. So it doesn't apply to some specific type of transformer. And whenever I talk about a limitation of recurrent models or SSMs, then it applies to a very general definition of RNNs, and it applies to multi-layer RNNs, and it subsumes all the architectures that are typically used in practice, like Mamba, LSTMs, and so on. And all the results that I'll discuss apply to,
So this means that you allow some, say, rational weights?
Yeah, so that was the next point, that all of these are with fixed precision or finite precision numbers. Okay, so the first task that we'll discuss is an extremely simple task. It's quite self-explanatory. And this task is also meant to explain basically some of the techniques that we later use to derive results for relatively more sophisticated tasks. So this task is called index lookup, where a model gets a sequence of symbols followed by a query index. So for instance, the symbols can be something like CZSTH, and given the query index 3, the model has to produce the symbol at index 3. For instance, here it's S, so the model produces S. So for this task, what we show, our first result is that one-layer transformers with width logarithmic in the size of the sequence length, let's say the sequence length is n, then transformers with width log n can represent this task. So basically, there exists a transformer with width O of log n, which can represent this task. On the other hand, any recurrent model or state space models requires a hidden state of size that is linear in n to represent this task. And this task is, even though this is very simple, this actually captures some of the core intuitions behind the kind of tasks which are easier for transformers but difficult for recurrent models. And it's straightforward to see that this task is quite easy for transformers, because when the transformer gets a sequence of symbols followed by an index, then using the attention mechanism, it can just attend or look up the required index and then produce the required symbol. And to show that transformers with log width can do it, we make use of something called almost orthogonal vectors to create or construct small size transformers. And for a recurrent model, this is difficult because they have a fixed size hidden state. They cannot look back. And when they get this sequence of symbols, they need to compress all the information in the fixed size hidden state in order to make a correct prediction when they get the query index. And this is something that we formalized based on communication complexity arguments that I'll talk about next. So this is the only technical part of the talk, and it's quite self-contained. So if I have lost you on something so far, then that's all right. This part should still be understandable. Okay, so let's look at the basics of communication complexity and how it's used to derive lower bounds. So the setup for communication complexity is pretty simple. So you typically have two parties named Alice and Bob, and their goal is to together compute a function f. So say there's a function f which goes from domain x to 0, 1, and input x is divided into two disjoint parts. Let's say Alice has one part of the input xa, and Bob has another part of the input xb, and their goal is to exchange as little bits as possible and then compute the output of the function on the joint input. And we first look at, let's say, a simpler version of the setting, which is called one-way communication complexity, where only Alice can send information to Bob, but not the other way around. So one crucial thing to note about the setup is that Alice and Bob can decide any strategy beforehand on how they'll exchange information, and they have unbounded computational power. The only information that is not shared between them is their respective parts of the input. And whenever we say that the communication complexity of a function f is whatever, say k or n, then what we mean is that Alice and Bob must exchange at least k bits to compute the output of the function for any input. So let's look at a couple of examples to understand this better. So let's go back to the parity problem, which we discussed earlier. So for the parity problem, let's say we have strings of length exactly n, and we need to check whether the number of ones is odd or even. If it's odd, then the output is 1. If it's even, then the output is 0. And let's say the input is divided into two halves, where Alice has the first half of the input and Bob has the second half of the input. So for this function, it's quite easy to see that Alice and Bob can compute the output by just exchanging one bit. So what Alice can do is, Alice can look at her part of the input, compute the XOR of the bits, or check whether the number of ones is odd or even on her part of the input, and can communicate that with Bob using just one bit. Bob can look at his part of the input, check whether the number of ones is odd or even, and based on the bit that Bob received from Alice, Bob can determine whether the number of ones in the entire string was odd or even. Right? So because they can compute the output for any input by just exchanging one bit, that's why the communication complexity of this function is 1. So this is, in terms of communication complexity, parity is one of the simplest languages or functions. So let's look at another canonical task called equality. So for this task, given two parts of the input, Alice and Bob need to check whether they are equal. So again, for simplicity, let's say Alice has the first half of the input and Bob has the second half of the input. But it need not be that way. Alice can have, let's say, the bits in the odd indices. Bob can have the bits in the even indices. They can partition the input in any way, but their goal is to check whether the two parts are equal. And for this problem, what Alice and Bob can do is that Alice can send all her bits to Bob. So Alice has n by 2 bits, Alice can send all of it to Bob. Bob can check his input and check the n by 2 bits received from Alice and can just easily check whether they are equal. And this is basically the worst that you can do, right? You can do this for any function. And usually the goal of communication complexity is to check whether you can do something better than this. And for equality, it is known, it's a classical result because of which we know that this is the best that Alice and Bob can do. Like, they have to exchange n by 2 bits, and even if two-way communication was allowed, even then they had to exchange n by 2 bits. And because of this, the deterministic communication complexity of equality is n by 2. Okay, so naturally, then the question is, so what does all of this have to do with RNNs and transformers? So now we'll basically discuss how we can use that concept to prove lower bounds for RNNs. And generally, the way the argument goes to use communication complexity to prove lower bounds is as follows. So what we'll argue is that if there exists an RNN that can compute some function f, and let's say the RNN has a hidden state of size m, then Alice and Bob can use that RNN to compute the output of the function f by just exchanging m bits, where m is the width of the RNN. And because they can compute the output by exchanging m bits, m is lower bounded by the communication complexity of the function. So that's broadly how it will go, but let's discuss the details. So recall that for a recurrent model, they have a hidden state ht, and they'll sequentially update it given input vectors x1, x2, and so on. And this ht is typically a d-dimensional vector, and because we are working with fixed precision or finite precision setting, so you can represent the d-dimensional vector using d times p bits, where p is your precision. So for simplicity, let's say m is the width, where m is order d. So m is d times p. So m is the number of bits that you need to represent the hidden state of the RNN. So now I'll describe how Alice and Bob can use the RNN to compute the output of a function by exchanging m bits. And the one basic thing to recall is in the communication complexity setup, Alice and Bob can decide any strategy beforehand. So both of them can use the RNN. So let's say there's an RNN that computes some function like the equality function. Then Alice and Bob can both use the RNN. And let's say Alice has the first half of the input, Bob has the second half. They can essentially have any prefix or suffix, but for simplicity, let's say Alice has the first half of the input. So what Alice can do is Alice can start with the initial hidden state, and given the first half of the input, Alice can sequentially provide the inputs to the RNN, update the hidden state, and compute, let's say, hn by 2 or hi minus 1. So Alice can update the hidden state based on her part of the input. And Alice can then send that hidden state to Bob using just m bits. And Bob can then update the hidden state using his part of the input and compute the final hidden state hn. And based on the final hidden state, Bob can compute the output. So now if this RNN computes a function like equality, then this m must be at least as much as the communication complexity of equality. So that's kind of the basic argument, and more generally what we have is that if a RNN with a hidden state of size m computes any function f, then that function can be computed with m bits of communication. And because of this, if we know that the communication complexity of that function is k or something, then m has to be at least as much as k. And now, like I mentioned, that the communication complexity of equality is n. And hence, any recurrent model that computes the equality function needs to have a hidden state of size order n. And similarly, the index lookup task that I introduced earlier, for that problem as well, we know that the communication complexity or the one-way communication complexity is order n, and that's why recurrent models need to have a hidden state of size at least n to compute that task.
I'm sorry for another question, but it seems to me that the model is just finite automaton. So this is just the size of finite automaton. You probably can achieve the same result without communication complexity. Just
So you meant we can achieve the same result with
the linear lower bound.
Yeah. So in the paper, so there's two ways of proving lower bounds for RNNs. So either you can do it this way, or you can also prove a lower bound based on their connections to automata. But that lower bound would be slightly weaker. So this, in some precise sense, this is a more stronger lower bound, the communication complexity based one. Okay, so we discussed one problem which is difficult for multi-layer RNNs, but it's easier for one-layer transformer. Now we'll look at a converse case, which is difficult for one-layer transformers, but easy for recurrent models. So this is called the bounded Dieck problem, where the model receives a sequence of two types of brackets, let's say square brackets and open brackets, and the model has to check whether the sequence of brackets is well balanced. But in addition to that, we have a constraint on the depth, which is the maximum number of unclosed brackets at any point. So it's pretty simple. We'll look at it with an example. So if you look at the first string here, that is in the language of Dieck 2 with depth at most 2, because it's well balanced. The second one is not in the language because there's a mismatch at the third position and also at the last position. And the third string is not in the language dig2 with depth at most 2 because there's 3 unclosed brackets, so it has depth 3 at a certain point. So the result I'll discuss now applies to dig languages with bounded depth as well as with unbounded depth, but this is the simplest one. dig2 with depth at most 2 is the simplest language in this family of languages. So for this problem, we know from previous works that recurrent models can easily represent this task. So there's even recurrent models of constant size. Once you bound the depth, it essentially becomes a regular language, and because recurrent models are closely related to DFAs, they can easily express this problem. But the main result in our paper is that any one-layer transformer that computes bounded dig language or even unbounded dig language requires to have a width which is linear with respect to sequence length. And again, for this result, we make use of communication complexity-based arguments. So the proof for this is slightly more involved than the argument for recurrent models. But in principle, we show the same thing, which is if there's a one-layer transformer that can compute a function f and it has a width m, then Alice and Bob can use that one-layer transformer to compute the output of the function f by communicating order of m bits. And because of that, the width of a one-layer transformer is lower bounded by the communication complexity of the function. But in this case, this is two-way communication complexity where both Alice and Bob need to exchange information with each other. So the first property is this. The second thing that we prove is that for bounded dig languages, the communication complexity is n-1 for a certain partition of input. And together, these two things imply that any one-layer transformer computing bounded dig must have a width which is linear with respect to sequence length. So essentially, this is a task that even small size recurrent models can do, but one-layer transformers need to be very wide. Now moving on beyond one-layer transformers, one interesting thing that we found is that for the equality task, where one has to check whether the first half is equal to the second half, for that problem, we show that two-layer transformers with polylogarithmic size or log width can represent this function, whereas based on the communication complexity results I discussed earlier, we know that one-layer transformers or multi-layer recurrent models need to have a width which is linear in n. So essentially, this gives us an exponential separation between two-layer transformers and multi-layer RNNs. But along with that, this is the first result where we observed a task which is quite easy for two-layer transformers, but very difficult for one-layer transformer. So two-layer transformers with log width can do this, whereas one-layer transformers need to be exponentially larger than two-layer transformers to compute the same problem. Lastly, coming back to the nearest neighbor task and the multi-query associative recall problem I mentioned a while ago. So for that problem as well, we show that two-layer transformers with log width can represent this function, whereas any recurrent model needs to have a hidden state of size that is linear in n. So this is not just a task which is empirically easier for transformers and difficult for recurrent models, but also theoretically recurrent models need to be much larger than transformers in order to compute this problem. Okay, so moving on to some final remarks. So the results that I discussed today, they stem from the fact that transformers and RNNs are very different as computational models. So recurrent networks, they have a memory vector that they can sequentially update. And because of this, it gives them the advantage of doing certain kind of state tracking tasks and even simulating DFAs. But the disadvantage is that for various kind of retrieval or lookup tasks, they need to compress all the information in a fixed size hidden state vector. Transformers, on the other hand, they don't have a memory vector that they can sequentially update or maintain, but they always have access to all input vectors, which makes it easier for them to do things like lookup, but it makes it difficult for them to do things like state tracking. Lastly, there's many open problems in this area. So for instance, the theoretical limitations of multi-layer transformers is not well understood at all. So for instance, I mentioned a task which is easy for two-layer transformers, difficult for one-layer transformers. So we have an exponential separation between two-layer and one-layer transformer, but we don't have any separation between three-layer and two-layer transformers. So that's a wide open problem. But there has been major progress. So there was a paper in Fox this year which proved separation from multi-layer transformers with causal masking. So that's one big progress that has been made. But for transformers without any form of masking, the limitations of multi-layer transformers are kind of wide open. Then there's a lot of open problems in precisely characterizing the expressivity of polylog size transformers, and people are also trying out things like hybrid architectures whose expressivity is not well understood and so on. And lastly, something that I'm quite interested in is understanding or identifying more problems that are relevant or indicative of practical performance. So for instance, the MQAR task that I mentioned, the multi-query associative recall. So even though it was introduced in a paper that analyzes models, that task has been used in several papers that design new architectures, including papers like Mamba 2. So it is being used by researchers who are designing new architecture as a proxy task at a small scale to make architectural choices. And kind of that's the only task that has been widely used in that manner. But identifying more such tasks is like a very interesting problem. Yeah, so that's all from my side. Thank you. I'm happy to try and answer any questions you guys might have.
Thanks for a nice and clear talk. And any questions? Anyone? Yep.
So as concerns this separation between layers, so there is this classical result by Heinau concerning threshold circuits.
Right.
So that you have separation even between two layers and three layers, the Boolean inner product. So probably this could somehow be transferable because you didn't show the details about the nonlinear function that you use. And so actually this concerns the Heaviside activation. Yeah, so and this is even true for polynomial weights. So not only for constant with weight, so probably it can be used here in this context.
There are also polynomial weights. These are not constant weights. So
sorry,
the precision is not constant. So the weights are also polynomial.
In this case, no.
All these results, the precision is not. It's finite, but it's not fixed. So the weights are not constant. So, but anyway, like the point you mentioned about threshold circuits, that's very relevant because the barriers to proving lower bounds for multi-layer transformers is similar to the barriers to proving lower bounds for threshold circuits with large depths. So for threshold circuits, we have lower bounds for depth 2. Yeah. We also have lower bounds maybe for depth 3, but not beyond 3. No. For depth 4, at least, we don't know much. But so there's some equivalences. For instance, for ReLU networks, for ReLU feed-forward networks, proving lower bounds for 6-layer ReLU network would imply a lower bound for depth 4 threshold circuit. Yeah. So that's a review. So proving lower bounds for some multi-layer transformers also has some of those equivalences because multi-layer transformer also has a feed-forward network within it. So one layer itself has 2 different blocks. So because of that, even though we say 2-layer transformer, but it's essentially 4 different blocks, and some of the barriers are similar. So we suspect, like other researchers in this area also suspect, that proving lower bounds for 3-layer transformers might be very difficult, but it might be possible to prove lower bounds for 2-layer transformers, but it's still, we don't have such a result yet.
It also depends on the class of function you consider. So if you have only Boolean functions or...
Yeah. We also, let's say we only look at Boolean functions.
There are also results concerning real functions, real valued functions.
Yeah, for
like
real
the maximum needs logarithmic. This is a conjecture, of course. I mean, it's logarithmic number of layers, and you actually need 2 layers to compute the maximum of n numbers.
Right.
Yeah, this is for rare networks.
Yeah, could be. Okay.
Yeah. Okay.
Thank you.
Any other questions? Yep.
Hey, thanks for the talk. I have a question about like the relevance of the formal grammars, because my impression is that, well, even though we can specify like very obscure regular language or whatever, it will be very distant from what human languages look like, and so we don't have any formal grammar to describe how longer texts look like. So the longer the text, perhaps the smaller the role of the grammar, and the sentences are just additive. So one question is, do you know about some formal model of like longer texts, and if this can be somehow modeled with the neural models? And the second question is, when you generated the languages, the form or the grammars of the formal languages, did you somehow consider if the sets of rules are plausible from like human language perspective?
Set of rules. Oh, sorry. What did you say?
Yes, like the grammars, the languages must have some grammar. So when you the grammar that you use, was it somehow like did you care about it being like?
So this was not. So you asked a couple of questions. So the first question was along the lines of like the relevance of these formal languages, and regarding that, like I mentioned, so it's not clear whether like this Chomsky hierarchy and a lot of these frameworks are particularly to model sentences, linguistic perspective, but we use these models on relatively much longer text and so on. So it's not clear whether those kind of results or those kind of analysis have direct implications on modeling natural language. The thing that they have implications on is like things like modeling programming language, for which these models are used quite a lot. And even there have been works which, so for instance, this parity or state tracking. So the parity language that I mentioned, where you just have to compute order, events, so the state tracking like task. So based on this, you can construct many Python programs which are easy for recurrent models to understand, execute, and so on, but not for transformers and so on. But coming to that, like over time, what I have at least like personally, what I have realized is like for the understanding the practical performance of these models, it's not necessary that these the categorization based on formal language is maybe like reflective of what happens with transformers, because for transformers they don't fit very well in this Chomsky hierarchy. They can do certain context-free language, certain context sensitive. They can do certain regular languages but not others, and so on. And that's why I find, so if you look at the tasks that I mentioned in the second part, so we try to move beyond formal languages and try to think of problems that are just practically motivated but just formally well defined. So for instance, this nearest neighbor problem, and the things that I didn't discuss was how nearest neighbor thing, that mechanism is also used quite a lot by LLMs. So that's also part of the paper, that LLMs actually emulate this kind of nearest neighbor behavior. Then this other paper also described how this MQAR task, this is actually something that creates a difference between transformers and non-transformer architectures. So that itself is like one of the most challenging things, which is understanding what kind of well-defined tasks are more reflective of practical performance. Because right now, the only way you can understand difference between two architectures is training a 7B model on a trillion tokens and then comparing them. But what we would also want is like some kind of these small-scale proxy problems on which we can train models from scratch and get some kind of signal that this maybe architectural choice is not the best one. And regarding your question on long context thing, I think people have made some efforts, but I'm not sure if any of them have kind of been more established. So I've seen papers, but I haven't, I sort of never read them properly, because maybe, people have made efforts, but I'm not sure if they are well established. So,
okay, thank you.
Thanks. Any more questions? We still have quite some time, half an hour at maximum. So while let me ask also one question, and that's based on the results that you said. Could we say that natural language tasks, those that people use, those that people require or ask LLMs to do they need more lookup than counting in a way? So is that like an empirical?
Counting is also something transformers are good at. They require more lookup and counting than, let's say, modular counting maybe.
Modular counting or bracketing. So
Yeah, so bracketing multi-layer transformers are also good at it. It's just one-layer transformers which are bad at that.
What type of, could you clarify what type of counting, which task was that exactly?
Yeah, so maybe I can give you some examples. So if you look at counting, so there's something like, let's say Deek1 language, right? So you are given one type of bracket and you need to check whether it's well balanced. So this is a contextual language because you can do it with a stack. But you can also do it without a stack by just using a counter, because what you have to do is when you get open brackets, you increment the counter by 1, and whenever you get closed brackets, you decrease it by 1. And what you need to make sure is that throughout, the counter should always be greater than or equal to 0, and at the end, it should be 0. So then it's in the language. So you don't need a stack for this. But for Deek2, you need a stack. So this is a context tree as well as a counter language. This is a context tree but not a counter language. So this is a language that both transformers and recurrent models are bad at, but people have developed these things called stack augmented sequence models, which are good at doing things like Deek2, but those models don't work well in practice beyond these formal languages. So nobody uses them. But
so this is what humans don't do based on the large language model training data.
Pardon?
Well, this is what humans don't do. Like Deek2 languages are not.
Yeah, so it's not. We also can't do it for very large lengths or very large depths as well beyond. For Deek2, I mean Deek2 because it's a very notable contextual language. It's from linguistics. It's always motivated quite a lot, like the center embedding stuff and so on. But we can only do it until a certain depth. We also can't do it for large lengths and large depths quite easily.
So then the language is formed so that we like stop and start a new sentence so that the depth doesn't, so that there are not so many bracket types in natural language text. Okay, thanks. And another question, which is just like random. You've talked about the weights precision, and you said that it should be finite precision, any precision but finite. So that corresponds to the current standards that we use, some particle floats representation.
Yeah. So basically, what we get when we do this, when we have these lower bounds, when I say, where is it? Let's say when I say that the size of the hidden state is omega n, what this means is that the product of the dimension and the precision, so d times p, that is omega n. So p can be log n, p can be, so it can't be linear in n, which is also impractical. Typically, we are either in log n regime or constant. Because we have 64-bit precision, right? So we will not have, if we are doing something over a sequence of length 1 million, we are never going to have precision which is 1 million, right? So precision will always be 64 or something which is log.
So my question was like, it's whether these various proofs are typically done with this realistic setting.
Yeah, because finite precision is more realistic, right?
Because there would be a worry that these results are theoretical in the sense that they require infinite precision.
No, so actually, so we particularly chose finite precision because that's closer to practice. Because if you look at infinite precision, things are very different. If you have in infinite precision, even a one-layer transformer can pretty much express every function. And these, so recurrent models are also Turing complete. They can also do many different things. That's because like infinite precision is kind of equivalent to having infinite memory. Because even if I give you one scalar and give you infinite precision, you can store like all the data in the world within that one scalar. So they are kind of equivalent notions. So fixed precision or finite precision is something that is more relevant. And for all the problems that I mentioned, like this index lookup, equality, nearest neighbor, so often the results on so obviously these theoretical results that do not imply that transformers or RNNs will perform similarly when you train them from models, but based on experiments, they also perform similar to what our theoretical results imply. Like if some problem is easy for transformers to represent, then they also learn it easily, which is not directly implied from the theory, but that happens just we check by doing experiments. The lower bounds have direct implications on learning because what we are saying is that if you take a RNN which has size less than this, like if you give me a sequence of length 1 million, I can tell you that if your hidden state is smaller than this, then it cannot represent it, and hence you cannot learn it as well. So the lower bounds have direct implications in that sense.
But any other questions from anyone?
Just a comment that the precision can also be somehow measured by Kolmogorov complexity, and by increasing the Kolmogorov complexity of these weight parameters, you increase the computational power of these models.
Right.
So I have one more question, and that is whether people also consider like hybridizing the two approaches, the recurrent and transform approaches, so that they would benefit from both the linear processing and at the same time.
I mean, empirically, it's a very active area, and that's like one of the open problems I mentioned towards the end in terms of like theory. There hasn't been a lot of work in understanding the representational capabilities of hybrid architectures, but empirically it's like one of the most active areas, and it may also have like a lot of impact, because if you look at recurrent or state space models from like 4 years ago, they were much worse than the ones we have today. So they are kind of catching up, and what many works have shown is that even with like a few transformer layers and many recurrent layers, you can get a performance that is very close to transformers. So but which is lot more efficient, because there's only a few attention blocks. The attention blocks are kind of bottleneck in terms of inference time, right? So it's a very active area, but they still haven't completely caught on. Even now, standard transformers are kind of like the go-to approach.
The best way to. Thanks.